In lesson 3.1, you'll learn to graph exponential functions. You'll learn about the natural base and then learn to graph natural exponential functions and their transformations. Let's begin by going over what an exponential function is. An exponential function is simply the relation where the base is a fixed number and the variable is going to be the exponent. So for example, f of x equals 3 to the x power is an example of an exponential function. However, f of x equals to x to the third power, that right there is not an example of an exponential function, because again here the variable is the base and 3 is the exponent. Another example of an exponential function would be f of x equals to -5 to the x power, because here our base b is a number that is greater than 0, a positive number greater than 0, and not 1. So even though we have a negative sign right here, our base is 5 to the x power. So here we're going to multiply a bunch of 5's together an x number of times and then multiply that negative sign with that. So for example, we'll do third power, f to the third power. That would be -5 to the third power, which means we're multiplying 5 3 times, and then that answer is then multiplied by a negative. Now compare that to f of -5. Oh, I'm sorry. F of x is equal to -5 to the x power. Here, our base is -5, which again cannot be true because our base always has to be a number greater than 0. And it cannot be 1. So in this situation, it would not be an exponential function. So this is not an exponential function. And another example of something that is not an exponential function would be f of x equals 1 to the x power. Again, our base has to be any positive number with the exception of 1. Because here, multiplying a bunch of 1's together is not going to give me a line that grows, a curve that grows. It's just going to give me, again, constantly the same value of 1. So it wouldn't make a difference if I'm raising 1 to the 10th power or to the 100th power. My answer for both is still going to be 1. So it's not going to curve upwards. It's going to just be a horizontal line and not an exponential situation. Now, while the format that we have here, before I move on to the next slide, the format that we have here for the exponential function is a times bx. The parent function in standard form, the simplest form of writing an exponential function is f of x. Let me change the pen size. F of x equals b to the power of x. Or we can write it as y equals b to the power of x. Again, our base, just to recap, our base has to be a positive number with the exception of 1. And this exponent here, our exponent could be any real number. It could be, again, 2 or -2. It could be 5 or -5. It could be 1/2 or 1/5. Okay, positive or negative. It could be any number that we want. Of course, in those situations, it will make it a little hard to multiply the number, the base b, 1/5 times to it by itself. But again, it's still considered an exponential function. So let's go over how do we graph these exponential functions. Well, to graph these exponential functions, what we do is simply evaluate them by plugging in numbers for our exponents. So using a T-chart just to organize our work, I'm going to plug in the following numbers: -3, -2, -1, 0, 1, 2, and 3 into this function, into the values of x for the function. Now, I'll start with the simple one, 0, and I'll start by plugging in 0 in for x. Well, 2 to the 0 power is equal to 1, just like anything to the 0 power is equal to 1. 2 to the first power obviously means just 2, and 2 to the second power means 2 times 2, which is 4. Sorry, I put that exponent in the wrong place here. So 2 to the second power. And then finally we have 2 to the third power, which means 2 times 2 times 2, which will be 8. Since these two equal to 4, multiplying 4 with another 2 gives us 8. Now the difference between having a positive exponent and negative exponent is that we are simply going to get the reciprocal of the respective, of the corresponding x value. So for example, if y equals 2 to the negative 1 power, by the negative exponent rule, we're going to get the reciprocal of our base, which right now the reciprocal of 2 is 1 over 2, and that changes the exponent from a negative 1 to a positive 1. Well, 1/2 to the power of 1 is 1/2. And you'll notice again the relationship between 1/2 and 2 is that they're reciprocals of each other. So if I plug in a positive 1 and I get the output of 2 on these exponential functions, then by plugging in a negative 1, I'll simply get the reciprocal of 2, which would be 1/2. And the same thing's going to be true with the other values. If plugging in 2 is 4, plugging in the reciprocal of negative 2 is going to give me, I'm sorry, not the reciprocal, but plugging in the opposite of positive 2, which is negative 2, will give me the reciprocal of 4. So that would be 1 over 4. And then the same thing with 3. If I plug in 3 in for x and I get an answer of 8, plugging in the opposite number, negative 3, will give me the reciprocal of that value. So 1 over 8. And again, we could just do this, the last one. So that would be 1 over 2 to the power of 3, which again is 1/2 times 1/2 times 1/2. And now you can clearly see that's how we end up with 1 over 8. 2 times 2 times 2 is 8. So now let's plot these points. So starting with this part over here, let's plot those points first. So we'll plot 0, 1, 1, 2, 2, 4, and then 3, 8. Now to plot this point here at negative 1, the y value is 1/2. So that'll be right there in the middle. When x is negative 2, the y value is 1/4. So that'll be 1/2 of 1/2. So that will be in the middle between 0 and 1/2. And then the last value, when x is equal to negative 3, the y value is 1 over 8. So that will be halfway from the last one. So if I connect these points with a curve, my graph will look like this. Now, interesting again to see is that no matter what numbers I plug in, remember, all I'm doing is multiplying, again, factors of 2 when I'm plugging in positive exponents. So I'm just multiplying a bunch of 2's together when I plug in a positive number for x. So there's no way that's going to give me again a number that's going to be equal to 0. So I'm never going to touch this line in this direction because obviously those values are getting bigger and bigger and bigger. Now when I plug in a negative number for x, notice that all I'm doing is multiplying 1/2. So I'm multiplying a bunch of 1/2s together when I plug in a negative number for this exponent right there. Well, multiplying a bunch of 1/2s is never going to give me a negative number. This answer, again, multiplying 1/2 with 1/2 with 1/2 and so on, is always going to end up being a number greater than 0, a positive number. So again, I'm never going to be below this horizontal line. And well, obviously, it's not going to ever equal to 0 because, again, we're multiplying a bunch of 1/2s. Therefore, what that implies graphically is that we have a horizontal asymptote on the x-axis. So our domain here, while it could be any number that I want from negative infinity to positive infinity, our range is going to be values of y greater than 0. Our graph is only going to exist again above the x-axis, which again is our horizontal asymptote. Now let's look at what the graph will look like when I take the reciprocal of 2 and see how that affects the direction of the graph and the way the graph is moving. In this example right here, because the graph is increasing from left to right, the values of y are getting bigger and bigger as I increase the values of x. This is a exponential growth function. This is an example of an exponential growth function, a function again that, as you can clearly see, is increasing from left to right. Now let's see what effect happens, or what's the effect by switching and getting the reciprocal of our base from 2 to 1/2. So using the same technique, we're going to draw a t-chart, and using the same numbers, we'll see what output values we get. So start with 0 again, and raising 1/2 to the 0 power is 1. Raising 1/2 to the first power is obviously 1/2. Raising 1/2 to the second power multiplies 1/2 with another 1/2, which is 1 in the numerator and 4 in the denominator. And then multiplying 1/2 to the third power multiplies 3 factors of that, which again is equal to 1/8. Now, having the exponents become negative simply is going to give me the reciprocal of the value. So starting with -1, that's going to give me the reciprocal of my base, which the reciprocal is 2, and that changes the exponent from a -1 to a +1. So that's 2. And then the same thing is going to be true with all the other ones. So -2, 1/2 to the -2 power would be 4, and -1/2, 1/2 to the -3 power is 8. So let's plot those points on our graph, and we'll start from here going down. So we'll start with -3, +8. -2, 4, -1, 2, 0, 1, 1 and then 1/2, 1 and then 1/4, and then 2 and then 1/4, and 3 and 1/8. So if I connect these points with this graph, my graph looks like a curve like this. And the same characteristics can apply. We first of all see that this graph is above the x-axis because the x-axis is a horizontal isotope. You'll also notice that what they also have in common is that the y-intercept is still 0, 1. And that makes perfect sense because at 0, since our variable again is the exponent, raising 1/2 to the 0 power or raising 2 to the 0 power both gives us again an output value of 1. So it only makes sense that we would both of these functions cross the y-axis at 1. Now, having gotten the reciprocal and having this number again be a value, the reciprocal to a value that is less than 1, we see that the graph again is decreasing in these situations. So this is an example of an exponential decay, which simply means is that our function is decreasing from left to right. So as you can clearly see here, the difference between having a positive base and having a base greater than 1, not because the bases are both positive, I misspoke. Having a base that is greater than 1 and having a base that is less than 1 is that if our base b is a number less than 1, still positive of course, so still positive but less than 1, then we're going to end up again with an exponential decay function. But if our base, if y is equal to a base to the power of x and that base is greater than 1, then we're going to end up with an exponential growth function. So it's all depending on what this base is. So multiplying again a number greater than 1 an x number of times is going to make the number bigger from left to right. Because obviously that makes sense. The more I multiply the number by itself, the bigger the number becomes. So that will grow it. However, if I multiply a number less than 1, like 1/2, then that's going to make the value smaller. And that makes sense, because if I have 1/2 and I multiply 1/2 with another 1/2, that's a fourth. Multiply another 1/2, that's an eighth. That number's smaller. And multiply by another half, that's going to equal to 1/16. So again, that number is getting smaller and smaller and smaller. So the more I multiply a half, the smaller the value becomes. And that again, as a result of creating an exponential decay. So that's the difference between having a base that is greater than 1 and having a base that is less than 1. Again, still positive though, but less than 1. Now, the most convenient of choices for a base is the irrational number e, which is named after Euler's number of 2.718281828 approximately. And this number is called the natural base. The reason this is called the natural base, because again, it exists in nature, as you'll see when we talk about compound interest and exponential growth and exponential decay models in the real world. We'll see what happens when we raise something to a very, very large value. We'll see that our growth rate gets very close to this value when we again multiply a specific base, a specific value to a high order degree. Now the function where we use e as the base to an exponential function is called the natural exponential function. Again, because of the base e, the natural base. What we're going to learn to do is learn to focus on how to graph these type of things, following again some key characteristics of exponential function. Now, again, mentioned again from the previous slides, we know that the graph of y equals a to the x, where a is going to be greater than 1, is going to create a graph again that grows. This is a increasing function, so growth, an exponential growth function. Now, some of the characteristics to all exponential growth functions is that their domain are all real numbers from negative to positive infinity. The range is going to be in quadrants 2 and 3, so it's going to be values of y greater than 0, and we're always going to intersect again the y-axis at 1. Now again, because the value of a is greater than 1, this function is always going to increase, and the horizontal isotope is the x-axis. And of course, it's continuous. Continuous again is directly correlated with the domain being in negative and positive infinity. Since there is no number excluded from the domain, then that obviously means that this function is going to be continuous. Now, using this and using this graph right here, we're going to graph natural exponential functions by transforming them and following again the rules of transformations. Now, this is what it looks like for exponential functions. If we're going to transform an exponential function horizontally, all right, we're going to either subtract an h value or add an h value to e to the x. Again, up here as part of the exponent. Subtracting an x value to the exponent of x, that gives us a graph of e to the x that is simply shifted to the right by h units. And this right here is going to shift it h units. By adding again this h is going to simply shift it to the left. Now if I want to translate it vertically, I either add or subtract again a k to the e to the x, not to the x but to the entire function itself. Adding it moves it upwards and subtracting it moves it downwards. A reflection could be horizontal and again vertical. If I'm going to reflect it across the x-axis, which is a vertical reflection, I simply multiply the function e to the x with a negative sign. And if I want to reflect it horizontally across the y-axis, I multiply the x of e to the x with a negative. Now, vertical shrinking and stretching again applies the same thing as before. It just simply looks like this with exponential functions. We have our e to the x and we're going to multiply a value of a. So that's going to stretch it as long as that value of a is a number greater than 1, and shrink it if that value of a is a number less than 1. Now the horizontal stretching and shrinking again occurs the same way as any other function, that we're simply going to multiply the input value with a value a. And it's going to, this is wrong. This should say stretch. And this one should say shrink. My apologies. It's going to stretch it if the value of a is a number less than 1, still positive, but less than 1, and it's going to shrink it if that value of a is greater than 1. Again, horizontally. It has those effects on it. So let's use again these right here in order to graph some transformations to these natural exponential functions. So let's start with something simple with a simple shift of 5 units upwards. So the plus 5 is going to shift this graph 5 units up. So we'll start by first again giving ourselves a point of reference. Let's say we have g of x is equal to e to the x. So let's graph that one. So g has a horizontal isotope at the x-axis. It's going to cross the y-axis at 0, 1. And we're just going to simply again just draw a general curve of what that should look like. It's not going to be accurate because we're only using this one point here. But this one point at 0, 1, we know for sure is going to be the same regardless of what the base is. Whether the base is e, 5, 2, 1/2, we know we're going to cross the y-axis there. Now, graphing f of x is going to get this function here and just simply shift it 5 units up. So this point is going to move 5 units up along with the horizontal isotope. That is also going to move 5 units up. So let's move the horizontal isotope first. So 1, 2, 3, 4. This is the horizontal isotope. And moving again in this point, 1, 2, 3, 4, 5. I'm sorry, I meant to say 5. I don't know why I counted 4. So let's move it 5. There we go. There's my horizontal isotope. Okay, now the point again, the y-intercept point of 0, 1 is also going to shift 5 units up. So that's going to now be here. So f of x again increasing, going to look like this. So this is what the graph of e to the x plus 5 will look like. It will simply shift e to the x 5 units up. Let's see, now let's look at a horizontal transformation, so horizontal translation. So again, just for a point of reference, let's graph g of x as e to the x. Let's graph that one. So that looks like this. Now the plus 2 is simply going to shift this function, this red function, 2 units to not the right, but to the left. So let's do that. Now, the horizontal axis being horizontal and shifting it to the left does not move, okay? So horizontal shift on a horizontal line looks the same. However, this point here is going to in fact move. So instead of crossing the y-axis at 0, 1, it's going to cross somewhere else, and this point is now going to be at this location there. And again, it's not drawn perfectly, but the curve is going to look like this. So it looks like it's going to overlap, but again, it's been shifted 2 units to the left. And just simply using this point as reference, as a reference point to count where the graph is going to move, that location that was originally at the origin is now at -2, +1. Now, to graph with a horizontal and reflection, let me first start by graphing again e to the x, just drawing a sketch of e to the x. The -3 is going to shift our graph 3 units to the right, and the negative is going to flip it upside down. So we're going to do those two things. We can start by flipping it and then moving it. So if I flip it upside down, instead of crossing the y-axis at 1, we're going to cross the y-axis at -1. But that only does one transformation, okay? That only flips it upside down because of the negative sign. That's going to reflect it across the x-axis. Now, shifting the graph over 3 units just simply means I need to move this point along with everything else 3 units to the right. So 1, 2, 1, 2, and 3. So I need to move this point to that location right there. So I'm going to do exactly that. I can grab the entire thing and just simply drag it. So let's do that. 1, 2, 3. And there's our graph. Let me just extend this horizontal part more. And well, this right there is good. Let me just put my arrow right there. And there. This is going to reflect it and slide it 3 units to the right. Or I can slide it 3 units to the right and then reflect it. Hence, I still end up with the exact same thing. And now here does 2 translations. It shifts the graph e to the x. Let me just draw that first. It shifts this graph e to the x 6 units to the right, to the left, and 3 units down. Now, the horizontal isotope is not going to be affected by shifting it to the left, okay? But it is going to be affected by shifting it down 3 units. So our horizontal isotope is going to now be at 1, 2, 3 at -3. However, our graph, our exponential graph, is not going to go through this point there. Because if I move it to only that point, that's only the shift of 3 units down. That's only this part right here. Let me do it in blue. That's only that part right there. Okay, moving it down 3 units. I also need to move it 6 units to the left. So I need to grab this point and move it 6 units also to the left. So 1, 2, 3, 4, 5, 6. And again, just drawing the general direction that the graph is moving. It's increasing. The graph is going to look like that. There's no reflection of any kind, so the graph should look something like this. We'll eventually cross the we'll eventually cross the y-axis somewhere. But again, we're just drawing sketches of this, so we don't have to be completely accurate. As long as we get, again, this key idea that the horizontal isotope is here at -3, and that at this point, originally located at 0, 1, is now correctly at -6, -2. Okay, -6, -2. That would be the correct location of that point. Okay, now let's work backwards and let's now look at an equation, graph, and determine again the equation for this natural exponential function. So I'm telling you again that the base, it's a natural exponential function, so f of x is equal e to the x power. Our base is going to be e because it's going to be a natural exponential function. So that means the base is e. Now normally this function again has a horizontal isotope at the x-axis, and it increases going through the y-intercept at 1. Now, if you look at the graph of this one right here, notice that the horizontal isotope is at 2. Y equals positive 2. And this point is now right there. It's now located right there at that location. So that means that the graph has been shifted and slid 4 units to the right and 2 units up. So the equation for f of x right here, this graph right here, is e to the x minus 4, that's going to shift it 4 units to the right, and then plus 2. So this is the equation to that graph. Again, assuming that the base again is the natural base, which I'm telling you again it is. So let's do another example. Let's do another example of a function that's going to have the natural base. So again, this is f of x. So we want to know what the graph for f of x is. Well, we know that the base is going to be e, so that would again automatically start us with e to the x power. Now normally e to the x power, however, looks like this. Okay? And well, there's 2 things again to look at first. The first thing, notice that the graph again is upside down. It's flipped upside down. So in order to flip it upside down, I need f of x to equal to negative e to the x. Okay? So right now, the red one, f of x equals e to the positive x, looks like the red one, and the blue one, which I'll graph right now, will look like this. So let me just simply draw it upside down. Okay? So that will look like that. So instead of trying to come up with, again, the graph for this one, let's look at this one and let's see how, again, this point, which is now at 0, -1, has been moved to. Well, we can see again for this graph here, let me highlight it in orange, this graph right here, f of x, has the horizontal asymptote at -2. And from the horizontal asymptote, I can see that we're crossing again this point that's normally at 0, -1, is located here at 0, -3. So that means it's only been shifted down 2 units. So that means that shifting this graph down 2 units is going to give us the function for f. So f of x equals negative e to the power of x minus 2. So there you have it. I know I'm using the same name, f of x, for all of them. I should probably use a different name for these functions here. So we don't get them confused. We'll call this one h of x in red. That's e to the x. We'll call the blue one, instead of f of x, let's use a different name for it. We'll call that g of x. G of x is equal to e to the negative x. And then again, the answer that we want is f of x, and that would be that one, the one in orange. This one right here. And there you have it. So what you want to do again with these examples is that you want to first determine again where this point has been moved. And on these examples, because it's upside down, you want to again look at the situation where we're going to have a negative and reflect it correspondingly. And I wrote the wrong thing here. This should not be, excuse me, that should have a negative sign on the e and not on the x, because the negative sign on the e would make it a reflection, but across the y-axis and not the x-axis, and not have it upside down. So I need the negative sign right there. And now looking from that perspective of this one upside down, I can then accurately count the reflection and how many units has been moved from its original location. All right, so this is again the end of the examples I have for graphing exponential functions and natural exponential functions. If you have any questions, please send me a message or remind. And like always, I appreciate you watching, and I hope you have a great day.